Now, this is an example of what we would deal with different categories and looking for different proportions. When this indicates when people report weights, they typically round to a whole number, so reported weights tend to have many last digits consisting of 0. You ask somebody how much they weigh, they say they weigh 170. They don't say that they weigh 171, things along those lines. Regardless of what they actually weigh, they tend to round it to a 5 or a 10 or something like that. In this experiment, however, we're going to take different people and weigh them on a scale and be precise to the nearest tenth of a pound. So we're going to look at it at the nearest tenth. We're not going to even look at the whole number of what a person weighs. We're going to look at the weights and only take the tenths column. So presumably we would have uniformly similar numbers. We should have as many that have 0.1 at the end as have 0.2, as have 0.3, and so forth. So we should have the tenths value be a 0, 1, 2, 3, 4, all the way to 9, and they should all occur with roughly the same amount of frequencies. So 80 people have been weighed, and the results are on table 11.2, which is on the next slide. Alright, so the last digit, again, this is the tenths column, being a 0 through a 9, and these were the frequencies observed. Now please note this value right here is less than 5. That's okay. Our expected counts will be higher than 5, so our observed counts don't have to be 5. So our requirements are satisfied. We randomly selected the 80 people, and the expected count should be 8. So we have 80 times 0.1. Each value should have 10% of the data in there. So 80 times 0.1 equals 8. And this value, 8, is greater than or equal to 5, and it's going to be the same for each different value. Now our null hypothesis is that all the proportions are equal to each other. In essence, we don't have any single greatest proportion in there, or single worst for that matter. The alternative hypothesis is that at least one probability is different. If at least one is different, then this fails. We weren't given a level of alpha, so we're going to use 0.05. And this is a chi-squared goodness of fit test. There's only one factor, and all of the requirements have been met. Now this is how the math works using the chi-squared test statistic. I'm going to show it to you like this, and then I'm going to show you how to use the calculators to solve for these. So in our first column we're dealing with, well, it's a second, but in our first real column that we're dealing with, we have the observed frequencies exactly as they were on the previous chart. Table 11.2 had them. The last digit is simply the category. It doesn't enter into the discussion or the calculations at all. We're only interested in what the observed values are. Now each expected value will be 8. Again, that is 80 times 0.1. That's where the 8 comes in. And this next column here takes each observed value minus the expected. So these are going to sum to 0 because they would have to, but you notice that anything that's below the expected will be negative, anything above positive, but once we square them they will all be non-negative. Anything that's exact will be 0, and otherwise we're going to square the values there. And this last column is taking the observed minus expected squared and dividing again by the expected, this value from this column here. And then the total of all of these is our chi-squared test statistic. Now how to do that in the calculator. Here's the instructions. So we want L1 and L2 to contain the observed values and expected values respectively. Those of you with the TI-84, we're going to run the stat test and then the chi-squared goodness of fit test. You're going to enter in the proper list, and I'll show you how to do that as well. For those of you who have a TI-83, we're going to in essence run that same mathematics that was done in the 3 columns of computations in the previous slide, and this is the function that's going to do it for you. You need to have the parentheses proper for this. So we've got the outside parentheses and we have an inside parentheses here for the squared value. Alright, now we're going to run the one-var stats with list 3, and that the sum of the x's will give us a total of that. Now let's see how this works. I'm going to go back a slide and show you the data. Alright, so this data must be entered in list 1, the observed counts, and these values are in list 2. Stat, enter. Now I've already got the data listed in here, but this is how it should look for you. Now, I'm not going to mess with list 3 yet. I'm going to come back to that. What I want to do is run this. This is an 84, and I'm going to show you the chi-squared GOF test for this. So it's stat, tests. I'm going to go up because it's near the bottom. And it's D on the TI-84s, the chi-squared GOF test. We will use this chi-squared test later, and the TI-83s have this value here, the chi-squared test, but they do not have the GOF test. So we're going to hit enter. We need to tell it the proper lists. I don't have them entered, so I need to change that. So instead of L2, L3, I've got list 1 have my observed and list 2 have the expected. Now this number is crucial as well. This helps you with the p-value. It helps you calculate the p-value. So we have 10 different categories, so this value will be 9. You need to make sure that you change that properly. Your test statistic will come out fine, but your p-value will be wrong if you left 5 or whatever the last time you had that in was. So this is our test statistic, the chi-squared, 11.25. As you can see, it's the same as it was here. And this p is your p-value. Now these here are the different values of the category. So you see 0.125 relates to this 0.125, 4.5, 4.5, 0.5, 0.5, and so forth. These are the lists of each of the individual values that contribute to the test statistic. So we've got a p-value of about 0.26. Now let's go to the lists themselves. Alright, now you have to highlight this list, this L3, and you're going to enter in the parentheses twice. We're going to give it list 1 minus list 2, and we're going to square that. Let me close parentheses and then square that. And now we're going to divide by our list 2 and close parentheses. So this is the function that I gave you. We're going to take list 1 minus list 2, square that, and then divide by list 2, which is observed minus expected squared divided by the expected. And this is going to populate each of these. And as you can see, the 0.125, 4.5, 0.5, they look exactly like they do here. To get the total of these, we run the one-var stats on L3. So stat, calc, one-var stats, we have to tell it list 3. And there is the 11.25, the sum of the x. We don't want x bar, we want the sum of the x's, and that's 11.25. Now, calculating the p-value, what we're going to do, and I don't have it listed there, but we're going to take this value will be our low in what is a chi-squared CDF. So let me go to that. Second vars, number 8 is the chi-squared CDF. It needs a couple things. It needs a low, a high, and a degrees of freedom. So it's much like the TCDF would. So our low in this case is the 11.25, comma, our high, we don't have a high, it goes off forever, so E99. And our degrees of freedom are 9, which is 10 minus 1. This will give us our p-value that we got before, about 2.2589 and so forth, so about 0.26. Now, if we're looking for a classical or traditional method, we're going to need an actual rejection region. So we've calculated the p-value. We already know the answer to our test using that method. But if we're looking at the traditional method, we take our degrees of freedom, which is 9, and our level of alpha, which is 0.05, and we match them up. And the value is 16.92. So anything above 16.92 for a test statistic, we will reject. Alright, so 16.92, or ish, whatever. There's our critical value. Everything in the pink over here will reject. Anything over here will fail to reject. We came out with a value of 11.25. It is less than that, so we fail to reject. And again, our p-value is 0.26. That is certainly greater than alpha. That would also indicate that we would fail to reject.